Differentiation of exponential functions. The natural exponential function y equals e to the power of x, first introduced in Chapter 8, is one of the most important functions in the theory of differentiation. It is the only basic function that is its own derivative. The famous Swiss mathematician Leonhard Euler defined e to the power of x as the infinite polynomial. So e to the power of x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the power of 4 over 4 factorial plus ... By differentiating term by term, we obtain d e to the power of x dx equals 0 plus 1 plus 2x over 2 factorial plus 3x squared over 3 factorial plus 4x cubed over 4 factorial plus ... So the derivative of 1 with respect to x is 0, the derivative of x with respect to x is 1, the derivative of x squared over 2 factorial with respect to x is 2x over 2 factorial, and so on. So now we can simplify. So we can get rid of the 0, we bring down the 1. Then we can simplify 2x divided by 2 factorial. 2 divided by 2 is 1, so we get 1x. And then we can simplify 3x squared divided by 3 factorial. So the 3's will cancel and leave us with x squared over 2 factorial. And then we can simplify 4x cubed over 4 factorial, so the 4's will cancel and leave us with x cubed over 3 factorial, and so on. And this is obviously the same as this, so therefore this is equal to e to the power of x. So d e to the power of x dx is equal to e to the power of x. So the derivative of e to the power of x is e to the power of x. So its derivative is itself. So if y equals e to the power of x, then y dash or y prime is equal to e to the power of x also. We can also use the definition of e to the power of x to approximate the important constant e. So e equals e to the power 1, which equals 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus ... This series very quickly converges or gets closer to approximately 2.71828. So we got these numbers from e to the power 1, so letting x be 1. So we have 1 plus 1 plus 1 squared over 2 factorial, which is 1 over 2 factorial, plus 1 cubed over 3 factorial, which is 1 over 3 factorial, plus 1 to the power 4 over 4 factorial, which is 1 over 4 factorial, and so on. The standard derivatives of e to the power of x and e to the power of ax are given on page 25 of the formulae and tables. So if f of x equals e to the power of x, then f prime x also equals e to the power of x. If f of x equals e to the power of ax, then f prime x equals a times e to the power of ax. So we bring whatever stuck on in front of the power down in front of the e. The exponential function can occur in products and quotients. So here we have the product rule and the quotient rule. So here we have page 25 of the formula book, and here we have our two formulas that we're looking at the moment, our two exponential formulas. Example: find dy dx if y equals 2x plus 1 e to the power of x. So since 2x plus 1 is stuck onto e to the power of x, they're multiplied, so we're going to use the product rule. So 2x plus 1 is the u, and e to the power of x is the v. So the given function is a product, so y equals 2 to the power of x plus 1 times e to the power of x. So dy dx equals u, which is 2x plus 1, multiplied by dv dx. So v is e to the power of x, so dv dx is also e to the power of x, plus v which again is e to the power of x, multiplied by du dx, so the derivative of 2x plus 1, which is 2. So since we have an e on both sides, we can factorize the e to the power of x. So we have e to the power of x times 2x plus 1 plus 2, and 1 plus 2 is 3. So we get e to the power of x times 2x plus 3. Chain rule for natural exponential functions. The chain rule must be used to differentiate exponential functions of the form y equals e to the power of u if u is anything other than exactly 1x. So for example, we would need the chain rule to differentiate e to the power of 2x plus 1, or e to the power of sine x, or e to the power of x squared plus cos x. Suppose y equals e to the power of u, then by the chain rule, dy dx equals d e to the power of u dx, which equals d e to the power of u du, multiplied by du dx, which is equal to e to the power of u times du dx. In practice, it is easy to use the chain rule on exponential functions. Write down what you're given and multiply the differentiating by differentiating the index. So here we have our chain rule number 4 for natural exponential functions. So d e to the power of u dx is equal to e to the power of u times du dx, i.e. what we're given multiplied by differentiate the index. So what we're given, the e to the power of u, multiplied by the derivative of the index, du dx. So we differentiate the power. Example, if y equals e to the power of x squared plus sine x, find dy dx. So what we're given is e to the power of x squared plus sine x, so we just write that down, multiplied by, so we have a dot for multiply. We differentiate the index, so the derivative of the index. So the derivative of x squared is 2x, the derivative of plus sine x is plus cos x, and this is our answer. So this is what we're given, and this is the derivative of the index.